Good morning, everyone. So we essentially looked at the introduction to the subject. Uh, we said three states of matter. We said why study fluid dynamics. Several examples were taken. Okay, and then we looked at some of these examples in a little bit more detail. Okay, like pollution in rivers and atmosphere, refrigerator, air conditioning. Okay, transmission of diseases, especially COVID disease. Then we looked at the process of scientific thinking. Okay, so we said that any scientific thing that we look at, it involves these few steps, starting from observation and coming back to some sort of a theory, and then trying to generalize that theory and see if that can be applied to other cases as well. And then from there, saying that okay, are there some new predictions from this theory that have not been observed, and then we try to go back and try to do those experiments. So it's a so it can start from anywhere, any of the boxes. Okay, typically starts from either of these two boxes, either from making observations or having a theory which is general enough, and that theory trying to or predict something new. So again, we had taken an example of all this through COVID as one of the examples, and illustrated these various processes that we undergo through, and then we also talked about there are three different approaches to solve any problem. We took a very simple example: theory, measurements, and simulations. And then we started asking us the question as to what is better, theory better than measurement and modeling, and or what comes first, measurement or modeling. And we can then ask also the question is why so much emphasis on theory. So we sort of, these are rhetoric questions. There is no right or wrong answer here. This is just to make you think and emphasize the point that theory is very important. Okay, because even the measurements that we make, the instruments which are involved in making those measurements are all built on some theoretical principles. Okay, so that is one reason why there is so much emphasis on theory anywhere that we look at. But that does not mean that the measurement, for example, is not important. Ultimately, the proof of any theory is whether it has been observed. The predictions that is being made by the theory are being observed or not. Okay, so this is a very brief introduction to what we had said. Then we said what's fluid versus solid. This is a question that was also asked. Okay, so we see that fluid will be solid deforms on applying a shear, whereas fluid will keep on deforming. So we do not talk about any maximum deformation that it can undergo, but we talk about the rate at which the deformation happens. Okay, and yeah, so here we we talk about a strain rate. That becomes a more important parameter for us. And then we talked about continuum. So everybody clear about this continuum hypothesis? This was the second question in the quiz today. Everybody clear about what we mean by continuum? So here we are saying that we are sort of neglecting the molecular nature of matter, and because molecular nature of matter is just too difficult, there are just too many number of molecules to deal with, and therefore we are going to deal with something which is a larger parcel of fluid, and then we take some properties around that. So and when we are able to do that, that's when we sort of say that we are in the continuum regime. So so here we are taking, for example, any property like density as mass by volume, of course, but volume tending to a small number. So we see that as we keep on changing this volume, the density or will change initially, but after some time or after some value of volume, it will stop changing. Okay, so that is now like the limit in which we can define this density. And here this volume is large enough that we are now including a large number of these molecules. Okay, so that's if you are able to do that, then it's like a continuum hypothesis is being satisfied, and we can work with the continuum because it makes our life so much simpler. So So these are some numbers to understand what we are talking about here. And then we said that we have a parameter, non-dimensional parameter, which is the Knudsen number, which is the ratio of the mean free path of the gas to the length scale. And when we say continuum, we are talking about 10 to the power of -3 and less the value of Knudsen number. Then we say that we are in the continuum regime. And we said that as far as this course goes, we will always stay in the continuum regime. And this continuum hypothesis allows us to say that, okay, all these field variables are a function of continuous functions of space and time. Okay, so this is where we had left in the previous class. So now we will, in today's class, in the very first 10 minutes or so, we will very quickly look at some of the important properties that are of relevance to us, especially we will be talking about viscosity. Okay, and then other properties, maybe surface tension a little bit we will discuss, and then other properties are there on the slide. I will not go through them, but I would like you to read them on your own after going home. And after that, we will start talking about the kinematics, I mean basically Euler. I mean we will essentially get into the subject after that right away. So okay, so this is classical parallel plate experiment. So you take two parallel plates, okay, or two plates which are very large, okay. So these two plates are very large means that along the length it's very large, and along the depth of the plate, along the depth or the third dimension here, the plate is very large. And we have two such plates, okay. The distance between them is finite, but these plates themselves are very large. Now you move one plate with respect to the other, okay. So this is now creating a shear, okay, as you can appreciate. So we are creating a shear, and we are trying to see what happens to the fluid which is sandwiched between this, okay. So normally you would have, if you don't do anything, you have expect to have air between them, okay, but you can put any fluid, water, oil, or any other fluid which is of interest to us, to you, and you can measure how much shearing has happened for this for the fluid which is in between them. So that is what has been shown here. Forces have been shown here, stresses have been shown here, and then you can first we have to understand, and this we are going to define little bit better. We have the no slip condition, okay. So what exactly is the no slip condition? I would like somebody to explain it to me quickly. So there is no, so what it means, no slipping, that there is no relative motion between the fluid and fluid which is next to the surface and the surface itself, okay. So that is your no slip condition, okay. So now how would you apply that to let us say uh, to flow on this over this disk? So what it means is the disk is stationary, is zero velocity. So and there are two directions in which we can have two. I mean, so there are three directions, of course, but two of them are parallel to this surface, and the one which is normal to the surface, right? So both these two tangential velocity components are zero, okay, on this surface, right? And what about the third direction, the normal direction? Yes. Yeah. Yeah. So what you are saying is right. So you are saying that there will be the fluid which is next to the plate will stick to the surface, and then the layer which is adjacent to that will retard, and so on, and there will be a boundary layer or a region which is affected by viscosity will form. So that is fine. So so that's like our no slip condition. So no slip essentially means that there is no relative velocity between them. So you can have a partial slip, for example. Okay, why it slips to the surface of the plate is not an easy question to answer. Okay, and I can tell you, if you look at the history of mechanics, you will be surprised that even Newton got it wrong. Okay. We like to neglect it, right? Hmm? Make it. So all the big names of mechanics, you can see they all got it wrong. Okay, so it is not an easy thing to explain.
Sir, and how big is this no slip layer? Is it 5 meters?
No, okay, so you can say how big is this layer? Okay, so that's actually a very good question. So you say that okay, it is next. So anything which is close to the surface. So what is the characteristic length scale? So that is already there. Answer is already there. So you are now saying what is the thickness of the layer which will be sticking to the surface. So you are now trying to define a length scale. If you think of it, you are trying to define a length scale. So what is the appropriate length scale to define for this case? So is the answer was the mean free path. Okay, so the mean free path of the gas is what is the right length scale to look at, and therefore the Knudsen number becomes important. Okay, so I will not get into this more. Okay, but you can say that there is. So if the mean free path of the gas is small enough, okay, then you would have the no slip boundary condition coming out to be fine. Okay, if the mean free path, as the mean free path of the gas increases, then you start getting into the slipping regime. Okay, and so okay, so if you are interested, we can just write down this relationship that the slip velocity, if you want to write it out, slip at the surface, if you this is something like lambda times some constant times lambda times dou u dou y at the wall. So if you know at the slip the gradient at the wall multiplied by the mean free path of the gas, okay, and multiplied by some constant, this is an empirical constant that you need to put in, and that will become equal to the slipping at the surface. So here what we are saying is that we have already seen that this is of the order of 10 to the power of minus 9 or 10 to the power of minus 8 meters. Okay, and so if that means that if this gradient is not large enough to compensate for this, I mean even if it is a few meters or hundreds of meters per second, okay, I'm still uh, not going to bother about it. So, so this is I mean, so that's why the slipping velocity that will turn out to be will be much smaller. You can say it is insignificant, and you can neglect that. Okay, so that's the answer to the question that you were asking. So you can see that liquids as well as gases are expected to satisfy this condition, and okay, so that is one aspect of this experiment that we are trying to do between two parallel plates, and one plate moved with respect to the other parallel to the I mean parallel to itself. Okay, that's the direction of the motion. Now what we are trying to do is look at this angle beta or delta beta and see what it I mean how we can do we can write down the something about this motion about this plate. So what we can do is tan delta beta is delta A, which was a displacement in the previous slide, you can see, divided by the distance between the two plates. So this is delta beta or delta A, sorry, and this is my B. Okay, so this tan of this angle is the ratio of these two sides, which I can say tan delta beta is like approximately delta beta. Okay, and then delta A is u delta t. Okay, so I substitute these and then I divide everything by delta t. So I get delta beta by delta t, which is like gamma dot. Okay, and so therefore I get u by b. The gamma dot is u by b, which is du dy. Okay, and further, so this is a simple relay. I mean, this is just I mean, in this case, we are able to see the strain rate very clearly. So we are just doing that and illustrating that. And then further, we are saying that this gamma dot, which is the strain rate, is going to be proportional to the stresses which are being applied, which is tau. Okay, and so we have not yet given this relationship, but let us say that this relationship is right. So they are directly proportional to each other. So we don't know that yet, but we are just assuming for now that they are directly proportional to each other. And therefore, if I now want to get rid of this proportionality and introduce a constant, okay, I introduce some constant here, constant of proportionality, which is like mu here. Okay, so you can see that that is how the viscosity gets introduced into my motion. Okay, so this is a very simple idea or example to illustrate how we are essentially introducing viscosity into the picture. Okay, but this is one of the key step is, of course, all this is simple geometry, which allows us to see that gamma dot is nothing but du dy, at least for the case that we are looking at. And then this is a case that we, or this is a relationship which we are assuming. And then from here, from this proportionality, we're changing it to inequality and then introducing this constant of proportionality, which is, we are saying is my viscosity. Okay. Any questions here?
Did we assume the linear velocity profile?
Yeah, so this is a, so this,
U by B is equal to du by.
so this we have already shown. No? This is already coming out from these equations. You can sit down and look at it more closely. It's already coming out from here. So
Du by dy, how is it?
because it's just u by b. Okay, in this case, u by b is nothing but, because it's a linear velocity profile. Okay, u by b is nothing but du dy here.
So linearly assume the rectangle.
Yeah, so here, okay, so we know that it will be linear. So here we are saying that this is a linear velocity profile that you expect to get. Okay, and in this case, so therefore you are changing this u by b to du dy. Both of them are the same in this case because it's a linear velocity profile that you have. Okay, so so this is how viscosity gets introduced in a very simple way. And now if you look at viscosity, okay, itself, we can have two types of fluids, and we are not going to get into too much details about the non-Newtonian part, but this is again something that I'm sure that you know about it. Okay, so when we have stress and velocity gradient or the rate of strain being directly related, okay, we call them as Newtonian fluid. When they are not directly proportional to each other, we will call them as non-Newtonian fluid. Okay, so if you look at the stress and the rate of strain, okay, so you can have that these are all linear and passing through the origin. So linear and passing through the origin is important here. Both these two conditions have to be met, but you can have these various lines, and these various lines are now having different slopes, and therefore the different values of viscosities to them. Okay, so if you have one of them would may correspond to crude oil, the other one with water, and something with to air, and so on. So again, I'm sure this is elementary, but we are just doing it again for the sake of completeness. Now, if you look at how this viscosity varies with the temperature, okay, so then you can see that at a given temperature, or as you keep on changing the temperature, then the viscosity would change differently for liquids as well as for gases. For gases, you can see that the viscosity increases. For liquid, it tends to decrease. And why it happens is related to the molecular nature of matter. Okay, so here, okay, so other thing that we can point out is that viscosity is only mildly dependent on pressure. For a major range of pressure, you can say it is independent of pressure. And even for gases, which is very surprising, and which is one of the first results why people started believing kinetic theories, it could predict that viscosity should be independent of pressure. Okay, and this is one of the examples where, because it was so surprising, people went in, measured it, and they found that indeed it is surprising for it is surprising. Okay, I mean it is independent. Viscosity is independent of pressure, which, as we said, was surprising. But this is what was being predicted by kinetic theory, and this is what also measured for a lot of gases. Okay, and so over a very large range of pressure, the viscosity is actually independent of pressure, but it is sensitive to temperature. Okay. Now, the other thing that I would like to point out is that if you look at the viscosity of water, okay, and this is the range that we are looking at. So viscosity of water actually drops drastically with temperature. So we are only looking at with liquid water, let us say under atmospheric condition, we are only looking at 0 to 100 degrees Celsius range of temperature. But over this temperature range itself, there is a huge variation in viscosity. And to give you some numbers, the viscosity decreases by 40% in the range of 15 to 38 degrees rise in temperature. Okay, so this is a huge variation, and it means that when we are talking about viscosity, viscosity temperature relationship is there. I mean, viscosity is so strongly dependent on temperature that you cannot neglect. For a lot of cases, you cannot neglect the change in viscosity with temperature. You will have to account for that if you really want to be accurate in your calculations. So this is one thing that we learn. Now, just for comparison, in the same range, if I were to look at density, density would only change by 1%. Density of water we are talking about. Now, the other observation that we make, as we have just said, that the viscosity increases with an increase in temperature for gases, whereas viscosity reduces with an increase in temperature for liquids. And this can be explained from the following. So, in liquid, there are cohesive forces, okay, which are resisting the motion between the layers, and these forces tend to reduce with an increase in temperature. So, that is why you would see a reduction. So, with an increase in temperature, the cohesive forces are reducing, because of which the viscosity is expected to reduce. And on the other side, on the other hand, if you look at gases, cohesive forces are actually negligible. What is more important are the exchange of momentum which is happening between the relative motion of the gas, between the various layers of the gas, and this exchange of momentum tends to get exaggerated with an increase in temperature, and that is why you expect to get an increase in the viscosity for the gases. Okay, so is this clear? So I think in some sense it's a very important slide. First of all, what we have done in today's class is very quickly look at how the viscosity gets introduced, and to say that we took a very simple example of two plates, one moving with respect to the other, and we showed that how the viscosity is actually coming into the picture in this case. Now we started saying that the viscosity, if you look at it, could be Newtonian or non-Newtonian. Okay, if you are looking at Newtonian, okay, you are going to get different slopes for corresponding to different liquids and gases. Okay, depending on what is the viscosity that they have, you will have different slopes. And now we are saying that if you look at the dependence of viscosity, okay, this is how it varies. With respect to pressure, it is mostly independent. With temperature, it varies, and it varies differently for liquids and gases. With gases, the viscosity increases with increase in temperature. With liquid, it tends to decrease with an increase in temperature. So this is essentially what we have seen, and we have explained why that is the case. And these are some relationships that can be used to find out how the viscosity is actually varying with an increase in temperature. So we don't have to get into this, but these are just put for your reference. Now moving on, we can say that if we are looking at non-Newtonian fluid, okay, maybe I can just pause and see if there are questions before getting further. Any questions here? So this is all elementary, right? I'm just going very quickly here because I hope that everybody is already aware of all this, right? Anybody is lost here? Because all of you are coming from different backgrounds. So if you are lost, please raise your hand so that I can pace myself appropriately. There is no point in covering so much and then at the end of the say, oh, we don't understand any of this. Okay, is this okay? Okay, so this is some movie which will show you that non-Newtonian behavior. I think we will not run it. But if you look at non-Newtonian, okay, you can have, so what it means is anything which is a straight, so here we are again looking at stress versus rate of strain. We said anything which is linear and passing through the origin, okay, is a Newtonian, but you can have all other types of, or so many different types of curves that you can have. Okay, so all of them which is not this straight line are your non-Newtonian fluid. And we know that air, water, these are the two most common fluid that we have, is governed by, is reason, I mean is or exhibit Newtonian behavior. Okay, even blood is non-Newtonian, okay, but at larger scales, if you are looking at flow in large passages, it is reasonably Newtonian. Okay, so it is like there is a strain rate dependence that it has. So, okay, anyway, blood is a more complicated fluid, but which is non-Newtonian. Really speaking, it is non-Newtonian, but a lot of times you can actually get away by assuming it is Newtonian. Okay, so what we are saying is that lot of common fluids, especially air and water, because those are the things that we are going to, as mechanical engineers, we are going to deal with. We deal with them most often. Okay, and even with some oils. Okay, so all of them exhibit Newtonian behavior. So we don't get into the non-Newtonian part. Okay, so non-Newtonian, if you look at the chemical engineers, what the fluids that they deal with are, I mean, they have non-Newtonian behavior, so they deal with non-Newtonian fluid dynamics in much more detail than what we do. Okay. So again, these are, you can have shear, thinning, shear, thickening fluid, you can have Bingham plastic and so on. Okay. So again, I will put up a small note for you. You can look at it if you want, but we are not really, as far as this course goes, we are not really interested in non-Newtonian fluids here. So we are not going to spend more time on it. Okay. Any questions about Newtonian and non-Newtonian, viscosity, etc.? Viscosity dependence on temperature, for example. Fine. Okay. So we can now talk about surface tension. Surface tension is something, again, it turns out that we will not really be using as part of this course. Okay, but it's important as a concept, as an idea, that we should be clear about it. So essentially it means that, I mean, the way we tend to understand it is that if we take a container which is water or some liquid, okay, at the interface, if you look at it, if you look at a molecule which is there at the interface, I mean, maybe first we can start off in the bulk. In the bulk, it is surrounded by molecules which are of the same type, and it is going to be pulled, let us say, in various directions, and all these directions, all these forces are approximately the same. So if you take an average over them, it is 0. Okay, so net force which is this particle would experience because of the adhesive force or the cohesive force rather between between these I mean, because of this cohesive force, net force will be 0 now. Okay, whereas now when you go to the surface, okay, then you see that at the surface you have attraction by one type of molecules, and attraction on the other side, there is attraction from the other side of molecules. Okay, so then you can see that there is difference, and this difference in the forces that is there will lead to, or can lead to, a net force. Okay, and this is what we describe it by surface tension. Okay, and it leads to stretching of the fluid solid interface, and it can lead to some interesting phenomena. For example, if you put a needle on the surface, so this is an object deliberately chosen which has a small mass. Okay, so you can see that the weight that is acting on this needle can be balanced by the surface tension force, and therefore the needle will not sink. Okay, so this is again a simple phenomena to illustrate that there is a force which is there, which is countering uh, the uh, the weight of this object. Yes.
So does this also depend on the Weber number?
Okay, so Weber number could be, I mean, we have not defined Weber number at all, for example. It will depend on velocity, etc., along with the surface tension value of the surface tension. Okay, so we are not really getting into Weber number for now. Okay, but what we are illustrating is that this is more like a problem of static. Yeah, everything is static here, and we are just trying to see, okay, can we have an object which is stationary or not? And so stationary means that there are no net force which is acting on it. Okay, here you can say that there could be some buoyancy force which is also there. Okay, so buoyancy force and surface tension force together are acting and countering your weight. Okay, so again, if you look at a surface, okay, I think this is one sort of an important idea that we need to sort of keep in mind, that if we have an interface and the interface is curved, okay, so if you are thinking about, like, for example, first to begin, like we have a bubble. So if you look at the bubble, and because it has a curved interface, okay, the pressure which is there inside the bubble and the pressure which is outside are different. Okay, and the difference of them is this value here. This is like your Laplace pressure which is there, and then you can take this idea and say that, okay, if the surface is going to be curved in general, if you have a wave, for example, there could be the pressure difference will be there between these two sides, and the difference will be because of this curvature that I would have at the interface. So I think this is what we need to know and understand, and we can, otherwise we can keep the surface tension thing aside. Okay, and interestingly, surface tension does not show up. We are going to drive our Navier-Stokes equation. It does not show up in the Navier-Stokes equation. Where will it show up? It shows up in the boundary conditions. Okay, so it does not show up in the governing equations. Okay, we have not done that. We have not yet drive the Navier-Stokes, but once we drive the Navier-Stokes, we will see that only the. So I mean, if you have to define, so there are maybe three types of forces. Maybe one should know. One is we have the body forces. Okay, the second one are surface forces, and the third one are line forces. So just going along the same direction. So we have L cubed volume, surface, L square, and then we have L force, which is your line force. Okay, so the only line force that we have is essentially the surface tension. Okay, the other two, so you have lot of examples of maybe surface forces. What type of surface forces? Surface forces are the one which are acting only on the surface. So pressure, viscosity, or the viscous effects, these are all acting on the surface. So these are all surface forces. Now what is a body force? Gravity, which is something which is acting. So every part of my body, for example, is feeling that the effect of gravity. Everything is being pulled down. Okay, and it is not just happening on my surface. Okay, on the surface, okay, one day I'm seeing what is the pressure. If there is some pressure which is acting on me, okay, that pressure will only act on the surface. It is not acting on my inner organs, for example. Okay, it can get transmitted, but that's a different story. But on the surface, on the body, the force is only acting through the surface. Okay, so those will be my body forces. So what we will realize when we write down our equations, that only the body forces and the surface forces will appear in the governing equation. What will get relegated to the boundary conditions, or all these line forces, or in fact surface tension is the only line force that I know, will get relegated to the boundary conditions. Okay, so that's where, so I mean, so that's why we can sort of safely close this chapter on surface tension, although it is important when we talk about capillary rise for droplets and so many other things. Okay, surface tension is not something that we can neglect, but there is a whole course on surface tension again, whole course on non-Newtonian, whole course on surface tension that you can go through if you are interested. Okay, now we can talk about compressibility, because somebody mentioned about this in the previous class. I'm just putting it here. Okay, again, I don't want to spend too much time on it. Okay, so what I will do is skip these things, compressibility as well as this coefficient of expansion, volume expansion, which is more to do with heat transfer, maybe some ideas of speed of sound, some vapor pressure concept, boiling. So I will just, I'm putting these slides again. These are like 1 or 2 slides just to remind you of the basic idea and the basic concepts which are there in fluids. Because we are not going to be really using them as part of our discussion, we are not getting into them. Okay. Now I will get to the subject of what is of interest to us. One, maybe I can just illustrate very quickly the idea of no slip with a figure here. Okay, no slip we have already just discussed. And again, what it means is, if you look at the surface, the velocity of the surface is 0, and here it is being shown by some hydrogen bubble. So this is I mean, this is a little bit of a digression, but let me just make that. So if you take liquid, let us say if I take water and pass current through it, what happens? What do you expect to get? You expect to get electrolysis. Okay, so an electrolysis, what will that create? Hydrogen and oxygen. Okay, so this is what is being used. So sometimes we use that for visualization purpose. Okay, so you pass current, we take a wire, pass current through that. Okay, so then you have water which is electrolyzing, and then you form this hydrogen bubble. So you can see that water which is flowing on top of that, you will have these bubbles. So you gave pulses to that. Okay, so you pass current for a certain time and then you stop it. So you have one pulse which is there, and you have one row of hydrogen bubbles which are getting convected with the flow. And then you give another pulse, and then you have another again row of bubbles which are getting convected with the flow. So this is how this picture has been created. You can see several rows have been there. Okay, this is my object. Okay, and these are my various rows of hydrogen bubbles which are there. Okay, is this picture clear? What we are showing here? So what is the what we are in no slip? What are we seeing here? So you can see that everywhere the bubbles are moving. Okay, here the bubbles are pretty much stuck on the surface. Okay, of course they are not infinitesimally small. Okay, they are in fact larger than the mean free path of the gas. Okay, so they would exhibit some amount of movement, which is what you see here, but of course the amount of movement is minimal as you can expect. Okay, is this clear? So it just illustrates the no slip boundary condition through a picture is what we are trying to do here. Okay. Okay, any questions before? So this is a very brief introduction to the course. And from the previous, I spent a lot of time in the previous time. So I got a feedback, don't spend too much time on it. We all know this. Okay, so this time I have really compressed it in 1.5 hours, less than, I mean, yeah, a little bit, like 1.5 hours. So it's like a very brief introduction. Anything not clear, anything which we need to go through it again. Idea of viscosity, the no slip. These are the two important concepts that we have looked at. Of course, we said surface tension is not important for us. We said non-Newtonian is not so important for us. Okay, so anything that we need to discuss? Okay, so if not, let's move on. So the first idea that we would really like to discuss here are how do we describe fluid motion? And there are two ways to describe that, Eulerian and Lagrangian. Okay, and I mean, as a small joke, I remember when I was introduced this topic, the professor said both of them were Lagrange. Okay, but it does not make sense to say it's Lagrange and Lagrange method. So we just said Eulerian and Lagrangian method. Okay, so this is just to sort of make you remember, or just to. So I mean, these are both. So these are two different ways of looking at the flow. Both of them coming from the same person, but we call the one as Eulerian approach, the other one is the Lagrange approach. So what are these two approaches? I would like somebody to tell me this. What do we mean by Eulerian? Lagrangian we track particles, which is right. Okay. Okay. This is not very precise. Okay, so I will not repeat that. Okay, so Lagrangian is following the fluid, that is for sure. Yeah, so that's right. So in Eulerian, we fix ourselves, we fix our position, and we see things moving past us. Okay, in Lagrangian, we move with the flow. So these are the two ways which we describe. So as a simple example, we can say, think of that we are in a train. Okay, so if we move with the train, then what type of an approach is that? The Lagrangian approach. Okay, now what is the other option? I can see stand on a platform and see trains passing by me. Okay, so then it becomes a Eulerian approach. So these are my two approaches that I can take. So which one of them do we normally take? Eulerian. And why is that? Yeah, so it is difficult to move with particles. Okay, so we fix our position, we stay at a particular point, and we start observing at that. Now, what is the complication that you can expect that will bring? So this is, if you understand this part, which I am just telling you in very simple words, it will give you a lot of conceptual difficulties you will not have later on. So simple thing, simple, when very simple language we are explaining it. So what is the complication that you expect because of which?
We get an average of another one volume.
Again, don't use very complicated average over control volume. We are not, simple thing can be explained. So what is the complication that we expect because of this? Hmm? Okay, Newton's second law. Okay. So what is the problem with Newton's second law? So there is a definite mass. If you say Newton's second law, F is equal to ma, how do I apply that? I need to apply it on the same mass. Correct? My mass has to be the same. That mass, my ball is accelerating. I say, okay, this is the acceleration of my ball. This is my mass of the ball. I multiply the two of them and I get the force which is acting on it. Right? So this is what we do when we apply Newton's law. Right? Now, what is the complication that I am now getting at? So if I follow with the particle, I am doing the same thing, no issues there. Now, if I decide to sit at a point, and why did we say we want to sit at a point? Because there are just so many fluid particles, I cannot follow them. So I am decided to sit at a point. So if I sit at a point, what happens? Different particles are now coming, right? I see different particles, I see different trains. If I go to the back to the analogy, I am now seeing different trains. Okay, so if I say that, so now what is the complication? What is my acceleration of my train? Okay, so what is my dv dt? Right? You see where I'm getting at? Because I'm now looking at one train and I'm looking at another train. Okay, at one instant I had one train, it had some velocity. At a different time, I'm looking at a different train which has a different velocity. Can I say the difference of these two velocities divided by my time is my acceleration? Acceleration of what? Which train? You can see that there is an issue here. Correct? And therefore, and I multiplied by mass of first train, second train. Okay, so you can see that this is where the issue lies. And this is where we need to be careful. Okay, and this leads to the idea of two different types of derivatives. One which becomes my local derivatives and the other one which becomes material derivatives. Okay, material derivative is what I related to my basic laws. Okay, the other ones I don't relate it to my basic laws. Okay, and then I have to derive a relationship between them. Okay, is this idea clear? Very quickly we have gone through this idea. Again, I will repeat myself. Okay, if you are not clear, please stop me. So we are saying that there are two ways to describe things. One, I am thinking of a train, I am thinking of a platform. I can sit in the train and I can move with the train. So if I want to say what is my acceleration of my train, okay, I just say that, okay, this is my velocity that I had earlier, this is my new velocity, okay, this is my difference in velocity over this much time. So this is my delta v by delta t is my acceleration of the train. And I know what is the mass of my train, so I know what is the force which has to act on this train, and I'm fine. There is absolutely no issues there. Okay, so this is one option that we have. This is what we have been used to studying and working with. Okay, normally this is the approach that we take. Now we say that if you want to do that, then if I am looking at a fluid, okay, fluid has so many particles, I will have to keep on tracking them. Okay, so every particle will obey the Newton's law, no issues about that, but then I have to follow so many of these particles. Okay, so therefore I am not able to do that. I don't want to do that. That's very inconvenient approach. So that is my Eulerian approach. If I do that, that's my Eulerian approach. But as we said, that is very inconvenient. So what do? I say that I am not going to move anywhere. I am going to stay here. Okay, and I want to describe all the mechanics sitting here. Okay, so that's my Eulerian approach. Okay, so then the equivalent of that is now I'm sitting on a platform. My trains are passing by me, and I just look at them and I want to describe the mechanics. What is happening to them? Okay, so now we can see that if I'm now talking about the acceleration, which is dv dt. Okay, what is my dv dt? Because first I'm looking at one time instant, I'm looking at one train, at the other time instant I'm looking at the other train. So I cannot look at the difference in the velocity of these two trains and say that, okay, this is my dvdt. It's meaningless. Okay, so therefore I need to write out. So you can see that I am now having two different types of derivatives. Okay, the first derivative we have defined is my total derivative of the material derivative. The second derivative which we are going to define is my local derivative. Okay, it's just valid at that point. It's just derivative of anything at that point. It is not corresponding to different particles or the same particle, sorry, it is just corresponding across different particles. Okay, so this is the complication we are looking at. Okay, is this clear? Okay, we are going to elaborate on this. This is just a very quick capsule of what we are going to see and why. Okay,
The total derivative is the total of the whole
so we are going to see that. We are, as I said, we are going to define this in a little bit more clear, but this is why we are getting into it. Okay, is this clear? Yeah, so sometimes we say that's a very loose statement. So when you say control mass, control volume, okay, control mass, thermodynamic, they say, okay, it's a, I mean, I just close the room in this and look at how much energy, how much momentum, etc. I have, I can do that. But let us say I now open it and everything is going, what does control mass mean? If my mass moves, I will move with that. Okay, if it go and I will now then define a volume which is encompassing, still encompassing all this mass. Okay, you can see it is meaningless. So I don't want to call it as control mass and control volume. Okay, although sometimes people loosely call it as control mass, control volume. To me, it is meaningless. Okay, so this is just a recap of what we have said. Property of the fluid can be described in two ways. In first, we specify the properties of function of space and time of particles which happen to be at location x at time t. And in this, this is my Eulerian description. Okay, and now if I'm looking at temperature as my property, is not the temperature of the particle which is at time t. Okay, rather it is the particle which happens to be at time t at this location x at time t and at time t plus delta t. Okay, so this is this is what we are looking at. This is the properties of this is what we are looking at. Okay, and we can sort of say that, okay, I'm just standing on a beach, okay, and breeze is flowing past me. Okay, it can come from different temperatures and I'm going to just feel that. Now when we look at the second case, the Lagrangian description, okay, here we are actually following the particles, and but this requires labeling the particles appropriately, otherwise of course we will get confused which particle we are talking about. So we need to label it. So now what is done is, how do we label these particles? Okay, so this is labeling is done by saying that this is the position of the particle at time t naught. So I say that, okay, I have to define some initial time which is my t naught. I say at this time this is where the particle was. So that becomes my label. Okay, and we are going to use that in a little, I mean, we are not really getting into a Lagrangian approach, but just to see the relationship between them, we will have to use it once. Okay, so that we understand the relation, and then this labeling will become important, and therefore I'm just we need to understand this point, that we say that, okay, this is where, so I'm saying, okay, you can see, for example, this fan is moving my air, and but if I just take, so if I take different time instant, of course, if I look at a given air parcel, it is moving and it is occupying different regions in space. Okay, so but I will say that at this instant, this is where the particle was. At this instant, this is where, at the same instant, this is where the particle was. And then once I have this, I have labeled all of them, then I can just let the fan rotate, and then I will see where all these particles go. Okay, so that is how I am going to describe in this case. So if I look at this quantity T of x naught and T, so this happens, this refers to a temperature of a particle which was at location x naught at time t naught. That's what it means now in this case, right? So I'm looking at time t, but I'm looking at particle x naught, which was at that, it was at x naught at that reference time t naught. Okay, so So this we know that Eulerian approach is generally preferred, okay, because following particles is difficult. And measurements, if I look at measurements, I can fix a probe and I can just look at what is happening at that, what is the temperature that it is finding at various times. Okay, I cannot move it along with the particle because I don't even know what is the trajectory of that particle. Okay, so you can see that if I try to do that, if I try to measure the temperature while trying to move with that, then it is going to become very difficult. So I'm going to now call the rate of change as measured by a fixed probe. We are going to call that as a local rate of change, and we are going to denote that as a partial of whatever quantity we are looking at with time. And the other one, which is the rate of change which is experienced by the particle, uh, uh, is, so if we move along with the particle, then the rate of change which is experienced by this particle is my material or the substantive rate of change, and we denote them with essentially d by dt. Okay, sometimes just to emphasize, in fluid mechanics we use capital D by the capital dt. Okay, it means exactly the same thing. We are talking about the total derivative here. Okay, so first of all, is this clear whatever we have said? What we are calling as what and why? So what we are going to do next is to write out the relationship between these two derivatives. Okay, no, labeling is just to sort of conceptual. I mean, I have to describe something, so I will think of that I've labeled it so that I can then track the particle. Otherwise, how will I track the particle? So let us take a very simple example and see how the two things get related. So let us say that I have fixed some arbitrary point. This is my x is equal to 0. Okay, let us say that we have one particle which is here at x is equal to 0, and the flow is going in this direction with some velocity v naught, some u naught, let us say. So let us say that there is another particle which is this one. I have just put it as some shaded thing. So this is, and I know that after some time delta t, the particle will come from here to here. Okay, so I want to now first label this. So at this is my picture that I see at time t is equal to t naught. Then what happens at, if I look at the time t is equal to t plus delta t, t naught plus delta t. So my first particle has moved here, and my new particle, the other particle has gone here. This is still x is equal to x naught, x is equal to 0. And so how will I describe these two, this system now? Okay, first what we want to do is put labels. Okay, and I'm going to put label at t is equal to t naught. Okay, so what is the label that of this particle? I know how much distance it is going to move. It is moving u naught into delta t. Okay, so this is, what is the current location of this? Minus u naught delta t. So this label I will put it as minus u naught delta t. The label of this is 0. Okay. Now what about here? Labels don't change, right? Labels don't change. Okay, what changes is the position of the particle. This is at x is equal to 0, and this position is u naught delta t. Okay, everybody clear? So now let us look at what is my, at x is equal to 0. What is it that I am going to see? So at x is equal to 0, I can see that the first I had this open or this white particle, and then I'm getting a black particle. So as we have said that we are going to talk about derivative is now being taken across different particles. Okay. So whatever is being, whatever was here earlier and now whatever is now, the difference of these two is what I would measure. Correct? Is this clear? So how am I going to write it out? So let us just see if I am to write it out with some so let us say I am just looking at any property eta. So this eta from the basic definition I can write it out as, I can say is equal to, so let me just go to the other board. Dou eta dou t. So what is my dou eta dou t? So it is whatever I have at the new time versus whatever I had at the old time, right? So I can write it out as x is equal to 0, t is equal to t naught plus delta t upon, or rather minus, eta of x is equal to 0 at t is equal to t naught upon delta t. Okay, so let us just be consistent in what delta t we use. So what symbol we use for delta? So let us just use delta t here. Right. So this is my basic definition of eta. So whatever I am looking at the derivative at x is equal to 0. So eta at x is equal to 0 at the two time instants. Okay. So this is what we have written. Now, but as we said that here we are now looking at different particles. So this is something which is not very satisfactory for us. So what we would like to do is to see how we can write it out for the same particle. So how can we write it out for the same particle? So what is there at this time instant? At this time instant, we have the black particle with us. And what is the label of that? The label of that is here. Okay, so let us change that. Let us substitute that. So we say that this is eta at x naught is equal to minus v naught delta t, comma t is equal to t naught plus delta t minus eta of, and what is this thing here? At t is equal to t naught, what was here at this part at this time? It was this white particle, and this white particle has a label of x naught is equal to 0. X naught is equal to 0 and time is equal to t naught. Okay, so all we have done is to go in from description of x to this description, and we see that they are exactly, we're talking about exactly the same thing, just describing them in slightly different ways. So now what we are going to do is to write out one term, add and subtract one term. Okay, so again I have used t is equal to t naught plus delta t minus eta x naught is equal to minus v naught delta t, and t is equal to t naught upon delta t eta x naught is equal to minus v naught delta t comma t is equal to t naught minus eta of x naught is equal to 0 and t is equal to t naught. So, all we have done now is to add and subtract a term which is this term here. Okay. So,
Sir, at second line you mentioned that t is equal to t naught plus delta v. X naught is equal to minus v naught delta t.
yeah,
That x
because
naught
the
is
time.
equal- X naught is equal to 0.
So, this is the label of the particle. So, what is here at this time? So, I cannot change time here. I am only changing the identifying it by different particle. This is the same. This is just a description. Yeah, so that's why the labels have been used. Okay, so the labels are corresponding to the previous position. The wherever we had labeled them. So we had labeled them at time t is equal to t naught, and at that time this particle was identified as minus v naught delta t, right? So that is what we are saying, that this is what happens to be at this position at this time. So we are just describing it in this manner here, right? So that's what we said when we put it, we label it at a particular time, whatever is the position that the particle is occupying at that time. That's my arbitrarily chosen. As like I've frozen that everything at that time. So wherever the particles are, I just say that that is the label that we have. Okay. So that's corresponding to the position that we have at that time. So sorry, this has been very unneatly written, not very tightly written. So, but you can see that from going to, so essentially that's how we go from this step to this step. Okay, so we are not changing the time, we are just simply describing it with whatever the particle is at that location. Okay, and we are just changing the label, and we are going from x to x naught. Okay, now in the next step, what we have done is added and subtracted this term, nothing else has been changed. And why we did this is because now we can write it out as two terms. Okay, first term would become this, what is common, and the second term will become this. Now, why are we doing that? So you can see that the first two terms are such that I am talking about the same particle. You can see that they are having, both of them are having the same label, which is V naught delta t. So both of and we are talking about the same particle now, but at two different time instants. Okay. Yeah, delta and delta. Yeah, this is all same delta. Yeah. Yeah. Sorry, I've mixed up the two notations. This is all the same delta here. X naught here. So you can refer to this figure here. Okay, so at this instant when I labeled it, this particle was at minus u naught delta t. Yeah, so that is when I have labeled it. So, so which term are we looking at? This term here. So we are changing this label here. So this is now becoming x is equal to 0. What is there at x is equal to 0? The particle which is this, which has this label. Correct? So that's why we have, that's how we have changed this. Similarly, when we go here, okay, at x is equal to 0, t is equal to t naught, what was there? The particle which was labeled at x is equal to 0. So that's what is there. So these two are exactly the same thing. We are saying exactly the same thing, right? Now what we are saying is we are adding and subtracted this term, okay, and what is now becoming common? The first two terms, if I look at, what has become the same? V naught delta t has become the same. Okay, so we are talking about the same particle now, but at two different time instants. Okay, now what is common between these two? The time has become the same, okay, but we are talking about two different particles. Okay, so this is how the math just works out very simply. So now if I have to describe these two terms, so the first term, which was eta at x naught is equal to minus g naught delta t, comma t is equal to t naught plus delta t minus eta of x naught is equal to minus v naught delta t, and t is equal to t naught divided by delta t. Okay, so how can I write this term now? Because we have already said that we are talking about the same particle and the change in property of the same particle. So this is d eta dt, right? Now let us look at the second term. Second term is, I'm just running out of space here, so I will have to remove this first equation, or maybe I just come on this side. So the second term that I get is eta at x naught is equal to minus v naught delta t at t is equal to t naught minus eta at x naught is equal to 0 and t is equal to t naught divided by delta t. So what is this term now? So here we are saying we are talking about the same time instant but different positions, correct? So if you want, you can we can go back and set it back. These are anyway the reference points that we have at time t is equal to t naught. I had labeled both these two things, and I can always go back from again in this description. So earlier what we did is went from x to x naught, and now what we want to do is maybe want to go from x naught back to x. Okay, for this term, as far as this term goes, we can do that, and we get this equal to x is equal to minus v naught delta t and t is equal to t naught minus eta at x naught is equal to, x is equal to 0 and t is equal to t naught divided by delta t. Okay, so now what you can see, what is the numerator now? So numerator is going to correspond to the change in x. So we are talking about two different x positions. So whatever is the change in the value of eta with x is what this numerator is, right? So it's going to correspond to that. So this is equal to whatever is the change dou eta dou x multiplied by delta x, right? So that's how you find out what is the, how much properties have changed from one point to the other point. It's just whatever is the difference, whatever is the gradient multiplied by whatever is the delta x, or the change in value, the values of these 2 points, right? And then divided by delta t. Okay. So now we can see, okay, any questions here? So now we can say we have essentially, that's why we went in from here to here. Okay, so here we are now forgetting about anything. We are just saying, okay, this is what is the value of eta at this point in the space, and this is the value of eta at this point in space. So the difference in these two values of eta, so the difference of these two is nothing but the gradient of that quantity multiplied by the delta x, right? So that's what we know. So we go back to that. So this is my how I get this term here, delta eta delta dou eta dou x multiplied by delta x, and then everything is of course divided by delta t. So finally, I have to put delta x by delta t is nothing but my velocity. And is it a positive velocity, negative velocity? What is my delta x here? So this is my negative x, and I'm going to x is equal to 0. Okay, so normally we go the other way around. So this is now going to come with a negative sign. So you can see that this is going to become dou eta dou x multiplied by u naught delta t upon delta t. So this is finally becoming u naught dou eta dou x. Okay. So here we get a minus sign because we have to just look at what is my initial and what is my final, and whether we are going from a larger to a smaller value or the other way around, right? Yeah, so right now we are just taking it as a very simple case. We are just saying everything is uniform velocity, but now we can, but once we get an idea between them, we can generalize this whole idea. Okay. So this is just to illustrate in a very simple 1D case, just to illustrate how the two derivatives are going to get linked. And then once we have an idea, then we can always generalize this idea. Okay. So if I put everything together now, I think we have running out of time here. So if we put everything together, what is it that we see? So we had on the left hand side, all that equation is now gone. And I think I will get rid of this figure here. So we had dou eta dou t on the left hand side, and on the right hand side we have two terms. The first term is here, d eta dt, and the second term is here, which is minus u naught dou eta dou x. Okay. Now we can say that this velocity is not constant, and in general, instead of having one velocity component, there are three velocity components. Okay. So we just did it for simplicity, assuming everything is constant, but we don't have to, they need not be constant. Then you can choose your delta t appropriately, and the same argument that we see here will apply. And similarly, if you're not moving in one direction, you're moving in all three directions. Again, the same very simple idea can be, I mean, this whole idea can be, this whole approach can be generalized even though to that case. Okay, so there is nothing which is stopping you from generalizing it. So that means that what you can do is, in general, so I don't have to assume this is constant. So I can in general say that dou eta dou t is, so this is what we can get upon generalizing it. Okay. So there you can see that this is how the two derivatives get related. And again, as we have said, why do we need to worry about that is what we have tried to explain in the beginning. Okay. So we said that when we go for an Eulerian approach, we are essentially talking about fixing a probe. So whatever is happening at that point is what the probe would measure. Okay, and this is what we do. We put a thermocouple, we measure the temperature at this fixed point, we put a pressure gauge, we measure the pressure of that fixed point. Okay, whereas what is actually happening is things are actually the properties which are being seen by that probe is not corresponding to the same particle. Okay, so and when we said that that is an issue, because when you apply our conservation laws are built for the same particle. If you look at Newton's law of motion, it is, we are looking at the same particle or the same ball which is traveling in air, and then we are just looking at what is the velocity, what is the mass of that, and then from there we determine the force. Okay, so whereas here we are doing a different approach, so therefore we need to find out what is the relationship between the two of them. And therefore, we did all this by labeling the particles. And when we label it, and then we saw that in a very simple case, when everything is moving uniformly in a single direction, okay, we can write out a relationship, which is this relationship here. And once we are able to understand this relationship, we can say that from here I can generalize it, and exactly this is going to happen. Okay, where we have said that this velocity need not be uniform, okay, and then the velocity need not be confined to a single direction. Okay, but then I will have, instead of the derivative along the x direction, I will have derivatives along the y and the z directions as well. Okay, so I think this is where we will stop, and in the next class we will start off with our next idea, which is our Reynolds transport theorem, and from there we will start driving our conservation laws.